Hey, what's going on everyone, this is Nikhil and in today's video I'm going to explain buffer overflows in detail with an example. As you can see in my previous videos on Stack Overflow, you may get confused because I did not explain that. So now I'm I don't own these rights. I took the rights from Open Security Training Info. Just don't copyright me for that. Okay, let's get started. First, we need to know the different formats, that decimal, binary and hex. In decimal, you will use the numbers in day-to-day life, just 0, 1, 2, 3, 4, 5, 6 up to 15. So these are decimal base 10. It means you take 0, 0, you add 10 power 0 press, 10 power 1 press, and you both add them, you get the result. In a similar way, 1, 10 power 0 into 1, 10 power 1 into 0, you both add them, you get 1. In the similar way, these are numbers are formed. In the same way as decimal numbers are formed with the base 10, binary numbers are formed with the base 2. It means the only two values you can take for a digit, that is 0 or 1, and this last b is the representation of the binary number. So you can see this as an example. It's ones press, tens press, hundreds press, thousand press. Now you can get decimal value by multiplying with the powers. 1 into 2 power 0 as it's in ones press, 0 into 2 power 1 plus 0 into 2 power 2 plus 0 into 2 power 3, and you can sum all those numbers, you get one decimal. In a similar way, you can get any binary value, you can get decimal value from binary value. So now another format is hex format. This is the base 16. The same way how you got the binary, you can understand this. The ones place is multiplied with 16 power 0 and tens place is multiplied with 16 power 1 into 0. So that's how you get the hex numbers. As you can see, from 9 it's normal decimal numbers, but from 10 onwards they're gonna change. As you can see, the value of 10 in hex is A, 11B, 12C, 13D, 14E, 15F. Okay, you need to remember this value. Just from 10 to it's gonna start with alphabets. So now negative numbers for the buffer overflows is not that much important, but let's just cover that topic. Okay, one's complement of binary number is flipping all the bits, so changing zeros to 1 and ones to zeros. In the same way, two's complement is obtained by adding 1 to one's complement. As you can see that example, take the first number 7 zeros and 1 binary, which is 1, and one's complement, you flip all the zeros to ones and ones to zeros, and you get this value. As you can see, this is the value is FE. Take first 4 bits, which is 1111. In hexadecimal it is F, and next 4 bits 1110, which is E in hexadecimal, which is 14. So now same way you can add 1 to this binary to get the 2's complement. Okay, has another important one is this 1 to 7 FFF is positive D-word, and for the memory space it's also called user land. From 8 to or FF to the end of the memory, it is treated as negative D-word, and this is in memory it's kernel and architecture. We need to know this is very important when we are looking at registers and stack, etc. So suppose there are two types of arranging the bytes in memory, that is little endian and big endian. So let's take the example 1 2 3 4 5 6 7 8 of hex. The least significant byte of a word is stored in the lowest address. That is, if there is increasing memory from left to right, the starting 7 8 is stored in the first memory, and 5 6 and so on, 5 6 in second memory, 3 4 and third, and so on. But big endian is just normal placing of bytes in the increasing order of memory. Suppose there are increasing, okay, next slide there is an example. So this is the lower memory address, this is higher memory address, memory is increasing. So in big endian you just place as it is, fe in the lower memory address, ed in the second, and so on. But in little endian we will just do the reverse. So this is the lowest order, we will place the CE in here, FA here, ED here, and FE here. So one main important thing is, in the registers it is big endian. It means that when you are looking at the EAX register or EBX register, you are looking as it is the value. But in the stack, the addresses are stored in the little endian. That means if you are looking at the value 1 2 3 4 5 6 7 8, it's reversed. So we need to memorize this point. Now registers are very important, and small storage memory built-in process. They are very fast. There are 8 purpose registers and instruction pointer. On x86 32 they are 32 bits long, and on 64 bit architecture they are 64 bits. So there are 4 main registers. EAX store function return values. It is also used for addition of numbers also in base register to the data section. This base register is also used for accessing arrays. Suppose you have the int a of 10, so say 10 integers array which stores 10 integers, then EVX is stored as base of that array, that is a of 0, and you just access the other elements by ECX which is counter for string, counter for loop operations, for loop, while loop. So you can also access array with EVX and ECX combination, and also with offset. Don't worry, for now we will just call that's the memory access methods, and EDX is the pointer. And sometimes EDX and EAX is commonly used for storing large values. Suppose if say addition or multiplication we got the more than 32 bits, so we store it in EDX and EAX. The highest most significant bits are stored in EDX, and next are stored in EAX. You may seem that accumulator register, base register, counter register. So you can see what is E. E stands for extended. So we need to know some theory before we just go on. CPU works in two modes. One is real mode and another is protected mode. So in real mode, any processor will work on 16-bit only. That is, when the computer boots on, it works in real mode, and later when your computer gets the login screen, then it goes into protected mode, that is 32-bit or 64-bit if your computer is 64-bit. So that's why they have extended the 8086 architecture. And there are another registers: source index, destination index, stack pointer, frame pointer or base pointer, and instruction pointer. source pointer for string operations. So you want to copy from one string to another string, some part of the string, you can name it as a source index, destination index. And ESP is stack pointer. Stack is data structure which we will be seeing in next few slides, and stack pointer always shows the top of the stack, and base pointer is shows the end of, no, initially. Okay, stack pointer shows the other end of the frame, base pointer is starting of that frame, EIP pointer to next instruction. So this is the main register which we are going to focus more in exploitation point of view. Okay, now let's move on. There are two different terms you can see, caller and curly. Caller means the one who is calling the function. Suppose in your main function of C program you may have written another function, so main will become caller and the function you call from the main becomes callee. So before main calls another function, it needs to store some values, because the function it will call can change the values. So caller save registers are EAX, EDX and ECX. So the main function will save the some values onto these registers and push, and then program flow transfers from main to the subroutine. That is the function it calls. And carry save registers are EBP, EBX, ESI, EDI. If there are, suppose there are, if the carry needs to use more registers, then carry is responsible for making sure these values are stored, and it should not also modify other values. Okay, that's all, just basics you need to remember for this. And here, as I said, first AX is 16-bit and this is extended into 32-bit. Further, AX accumulator register is divided into two parts, and first 8 bits you can access by accumulator lower, and another 8 bits of that 16-bit you can access by accumulator higher. In the same way for ECX register, the lower part 8-bit is called CL, counter lower and counter higher. In the same way the other general purpose registers also. Now flags are important when an addition operation or certain operation is done. These flags are set: 0 flag, unsigned flag, parity flag, overflow flag and so on. You can see more, there are many number of flags. Suppose if any subtraction between two operands results 0, then 0 flag is set. Okay, as the slide gives the star, had the star, it's somewhat important. That is NOP instruction, no operation, no registers, no values, do nothing. It's just passing, just continue in your Python program or pass in your Python program. You can see just when in if loop you write if the condition satisfies, just continue. The same way, no operation, nothing is done. And NOP instruction makes exploit more reliable. We will see that in our example. Okay, now we will discuss about the important one, that is stack. Stack is data structure last in first or data structure. Data is pushed onto the stack and popped. These are the only two operations that can be performed on the stack, that is push and pop. Push pushes the value something onto the top of the stack, and pop automatically pops the top of the value into the certain register it specifies. Stack grows from higher memory to lower memory. As I said before, stack pointer points to top of the stack, the lowest address which will be used. The lowest address, because the stack grows from higher address to lower address. So ESP automatically will be lower address which is the top of the stack. So stack keeps track of which functions are called before the current one. It holds local variables and frequently passes to arguments. So what it means is, if there is a function called main and it calls a function subroutine 1, and the main stack is stored and the new stack frame is created for the subroutine 1, and if any subroutine 2 suppose is called by subroutine 1, then again new stack frame is created for the subroutine 2. When it returns, that means the function subroutine 2 is over, then the stack frame destroys and then program flow jumps to subroutine 1. So whenever again this subroutine ends, it stack frame destroys and the control flows from subroutine 1 to main. Don't worry for now, we will look at some diagrams and we can understand more. Push operation is done on a stack. It will push the value you are specifying onto the top of the stack. Push word, dword, code word. Okay, you may see when you are typed f dword, that stands for double word, keyword for hard word. The push instruction automatically decrements the stack pointer ESB by 4. Why decrements? Because the stack grows from higher memory address to lower memory address. Okay, just concentrate here. Our stack is here before. ESP points to top of the stack, that is this address has this value, and I have EAX and ESP points to this value. I want to push EAX, so I want to push this 3 into the stack. So ESP is decremented by 4 and then 3 values pushed onto the stack. Now ESP points to this address and have the 03 value here, as here can stack after, and ESP is changed to this address. EAX is as usual because we did not modify EAX, we just pushed onto the stack. Pop value, the another operation performed on the stack other than push is only pop. Pop just take the value and put it in register you specify. So I have this stack before, I have 3 elements 1, 2, 3. ESP points to this address. So when I say pop EAX, pop take the top value and put it in this register, whatever register I specify. EAX pop take the top value which is 03. First 03 into EAX and decrements is ESP by 4. So now ESP will point to this address and this is undefined. As you can see in the brackets, it's still 03. The value is not deleted, it's just unreferred. It's not pointing, that's it. The memory still lies. So you can see EX before whatever the value may be, but now it's changed to 3 and ESP is decremented by 4. So if you just understand this simple concept and buffer overflows, you can understand very easily. So calling conventions, there are many types of conventions: C declaration, standard declaration, and this call, fast call. So those are almost similar, just with few modifications. So first we will see C declaration. See, as you can see, function parameters are pushed on the stack right to left. As you can see, func of arg1, arg2, arg3. First arg3 is placed and arg2 and then argvent1. Saves the old stack parameter and sets up new stack frame. Okay, first it stores the old stack frame of the main caller function and then sets up a new stack frame. Now EAX or EDX returns the result of primitive data types. Caller is responsible for cleaning up the stack. It means that after the function return, the function who called the another function is responsible for cleaning up the memory. Don't worry, we will see in the diagrams. Okay, standard call. Okay, this convention used in maybe Visual Studio. I have seen this. Okay, first it saves the old stack pointer and sets up new frame as same in the C decl, but here card is responsible for cleaning up any stack. It means that when you are about to return to the main function, return to the function card, the card will clean up the stack. That means you can see return 0x8 or something like that. It means that it is returning, and at the same time Kali is destroying the stack. That is standard call convention. Now call procedure. Call's job is to transfer control at different function in a way that control can later be resumed where it left off. It's just like call this function name. So the control flow from that point of instruction to that function, and then again returns to back to the next instruction. Okay, here you can see then it changes EIP to the address given in the instruction. As EIP, I have said that its instruction pointer, it points to the next instruction. Okay, destination can be specified in multiple ways: absolute address, relative address. Absolute address means it's normal virtual memory address, and relative address is relative virtual address. It start from image base. The generated program is loaded at 4 lakhs hex or something, and then you can calculate the relative virtual address. Okay, we will see all that stuff. And return from procedure. Pop the top of stack into EIP. The instruction is return. Okay, return, you can say pop EIP. They both are same. Return is actually places the top of stack into the EIP and then returns to the caller. Now, as I said, the standard declaration, you can see read 0x8 or 0x20. It means that it's standard call functions. So move operation. Okay, it name implies move, but it copies the values. It does not move. Okay, copy paste, not cut paste. Can move register to register, memory to register, register to memory, immediate to register, immediate to memory. Now memory to memory in 32-bit. Okay, now we have the main stack frame, and it has some local variables. Now whenever it is about to call a function, it saves some of its registers in EAX, EBX, ECX. As I said, card save registers and arguments to pass to card. Arguments which, suppose say it's calling subroutine 1 of 1, 2, 3. So 1, 2, 3 are placed in the reverse order 3, 2, 1. And then caller save return address. So you are confused about this. That's simple. Caller save return address means after executing your subroutine, so the next instruction in the main function should be executed. So that address will be stored here, and then it creates the stack frame. Sorry, it saves the main frame pointer, and then it creates the stack frame for this subroutine foo. As you can see, it's saving some registers and local variables, and now it's saved frame pointer and save register local variables. And if again in turns foo is a caller to any other function, so it will save registers and it will pass the arguments, and then it is as usual like in the same. So now this will act as main function or call to the subroutine which is going to call. So let's say these are 3 functions. Main has created the stack for foo has created stack for bar, and after that after function return stack was destroyed, and control flow jumps from bar to foo and foo to main. In this stack frames are linked list. Linked list is data structure which contains the data and pointer to the next node, and that's more of a data structures. Okay, first example you can understand with an example with clearly. So I have main function, it will call the sub function which return beef, and main function return food. It's simple x86 instructions. Push EBP, move EBP, ESP. You will come to know these are the, as you can see. Okay, first I will explain the theory. Push EBP, what is this? Okay, push the stack frame pointer of main onto the stack, that is saving the frame pointer of main onto the stack, and move ESP to that, and move EBP to the ESP. Okay, there are two conventions which you need to, that is inter syntax and AT&T syntax. In inter syntax, you move EBP ESP, it means that you take the value of ESP and put it in EBP, copy it in EBP. This is the destination, EBP destination, ESP the source. So you take the copy value of the ESP and copy it into the EBP, that is inter syntax. And AT&T syntax is reverse, which is the source and destination, but we will talk about inter syntax in this tutorial. And also inter syntax is widely used. Now we are calling the subroutine, and subroutine contains these instructions: push EBP, and saving the stack pointer, and same. As you can see, beef value is stored in EAX. As we have said that EAX is used for storing function return values. As the function is returning beef EAX, it is stored in EAX and pop EBP and then return to this main function, and then return to the exit the function. So we will see how the stack works. So I have some arbitrary values EAX, EBP and ESP. This is my x86 instructions code and my stack. Okay, let's say this is one certain frame before main, the PE loader of which called the main. Okay, now we will execute the first instruction, push EBP. EBP value is 12ff8. We are going to push onto this. Okay, the red color ones are modified value, green are start values. Okay, now move EBP to ESP. Take the ESP value, copy it into EBP. Now EBP gets changed by 12ff68. Nothing changes to the stack, just we are copying the value and put it in here. Now we are calling the function. Okay, before calling the function, we are saving the address of the next instruction to be executed in the main, that is 401018 onto the stack, and then jumping here. Now we will execute the push EBP. ESP is decremented by 4. ESP points to 60. Now EBP is pushed onto the stack. As you can see, ESP points to 60 and EBP is pushed onto the stack. Now copy the ESP into EBP. ESP is this value and we are copying it into EBP. So nothing changed except EBP. Now the value 0x beef is copied into EAX. Now there is nothing we are going to change on the stack, just we are putting beef into the EAX because EAX is used for function return values. So one more important point is you can use EAX register for anything, EAX like anything. So they just define EAX for function return values and addition operation, because if you return an assembly code and suppose if another want to understand the code, you should use the standard convention, that is, suppose ECX use it for counter but you have used it for addition operation, so that may be confusing for others to understand. So that's why we just follow the standard convention. Now we are copying the ESP into the EBP. Okay, sorry, beef into EAX. Yeah, beef into. Now pop EBP, press this into the EBP, and we are clearing up of the stack. Return. As you can see, this is the instruction. Before pop EBP, this is all the stack that belongs to this sub function. So we are clear of the stack, and we have this return called as return address return. Now push the EIP. Okay, I did not mention EIP here. Now EIP points to this 0401018. Now EIP function program flow transfers to this instruction. Food into EX. As you can see, food into EX, pop EBP, clearing of the main stack frame and return. So our program fully terminated. So that's all you need to know for basic buffer overflow exploits. I think you have understood the stack well. Now I'm gonna explain just briefly what is buffer overflow. As you can see, this is the stack. As you can see, this is the stack and these are the values. The application, the program, whatever you uses will use this stack. So now if we fill up with this buffer with all S, the stack will overflow with S. Of course all the registers, and of course EIP. Why EIP? Because it's instruction pointer and it's important for us. It can control the program flow. That's how we will get the basic EIP override, instruction pointer override. Okay, just a minute. Okay, now we are going to into practical example. One of those software easy rm.mp3, this version is needed for this tutorial. Don't worry, I will put all the links below in the description, and a debugger and mona.py. She's like Swiss Army knife tool for exploitation, and Python. Just you need to know Python, and find jump. We need to find some jump instructions which will jump to our shell code. Shell code is nothing but the code which you executes and gets the shell or something you decide is called shell code. And Metasploit basics, you don't need that much Metasploit basics for now. So okay, let's get started. So I have set up our environment. I am using Windows XP. It also works in Windows 7 32-bit and Kali Linux 2019 version. See, I have installed the easy RM to MP3 converter. You can just install from the download link. Now I have installed the immunity debugger, which is free from its official website. Of course, easy RM to MP3 is also free. And I have downloaded mona.py, and we need to put in the immunity debugger location, that is my computer. C program files, where is that immunity debugger? Yes, immunity debugger, 5 commands. As you can see, where is the mona? Okay, I have pasted it somewhere, mona. Okay, we need to first check there is any buffer overflow vulnerability or not. We can overflow entire registers stack without desired value or not. For that we need to know about fuzzing. Fuzzing is just simply, I'm gonna explain in one line. Just we give random input and also heavy input to check the application crashes or not. So remember one thing, every crash does not lead to exploitation, but we will figure the way we can exploit. So okay, let me log in onto my Kali Linux. Okay, sorry, this is somewhat slow, almost. Okay, so now I want to create a Python file. Sorry. Now EasyRM to MP3 converter has a vulnerability that if we feed the input into the M3U file, and whenever it opens, if the application crashes, we can check the registers and stack for buffer overflow. So suppose let's say print a into 10,000. Python 3 new.py. Okay, 10,000. We will output this into the any file name, but the extension should be m3u, test.m3u. I have this test.m3u. Okay, sorry for this time consuming. I don't know why my shared folders are not working. I messed up with that virtual network adapter. Okay, let's open this EasyRM to MP3 converter. Let's open that. So the application did not crash, the input was handled. So let's again try with let's increase our input. Let's set on 20,000. Okay, even for 20,000 is the application did not die. So let's increase another 10,000. So now test M3U have 30,000 bytes of A. I hope no application crashes. Okay, crashed and Windows has done the exception handling. Okay, done send. Now let's load up the immunity debugger. Now you can just open the file or attach to the already running process to view its registers, instructions, and stack. Okay, let me open the easy rm to mp3 one converter. Okay, I have opened it. So first, okay, I will quickly explain the interface. Here you have the x86 instruction. This is memory address, virtual memory address. Actually the virtual memory, the process understands that it's or the RAM is given to the process itself. That's called virtual memory, and it's handled by OS and CPU. So now these are the opcodes for this instruction. So whenever this opcode is encountered, the CPU execute this instruction. These are the lowest level of instructions than assembly language instructions. And here you can see the comments. Here these are the registers, as you can see, EX, EBX, EDX, and so on. And here the stack frame, and this is the memory dump. So let's run the program. Okay, program is run. Now let's input the test.m3 you have created. As you can see, everything were overflooded with A's. 41 you can see in hex format, that is A. As you can see, everything in the stack is A. Even you can look at EIP is A, at ESP is A. So we need to control the EIP to our shellcode, which pops a calculator or something. Then we win. So what part of AS is EIP points to? Okay, just can't go and say what number of A's starting we need to, the EIP is pointing to this or this or this or this. So for that we need to create a unique pattern such that any substring of the pattern should not repeat in the entire pattern. Okay, it's little bit confusing. Okay, for that we will use Metasploit pattern generator, which creates a unique pattern. Okay, one thing I need to say is the application crashed between 20,000 and 30,000 years. Let's give input of 25,000 years. Okay, debug, restart. Okay, now we will paste into this. Oh, application has entered the S. So now the input which you are giving in between 25,000 and 30,000, the application gonna crash, and the entire registers are overflowing with S. So now what we will do is we create 25,000 A's and 5,000 unique pattern, so that we can get the offset of EIP and ESP. For that, locate pattern, sorry, the location from at Kali Linux to the 19 has changed for the USB for pattern create or Ruby file. Ls, now we are going to use pattern create RB and the length 5,000, right? Just forgot the syntax. Okay, length, all right. Okay, it has created. Oh, I need to copy and enter this. Okay, another method I also show you to create a unique pattern. Copy. Another way to create a pattern is you can use the online tool or pattern generator. Similarly, you can use 3000 and generate. Here you get the overflow pattern. You can just paste it and you can find the offset. That simple one. Now we are going to create 25,000 A's and 5,000 pattern. Let's say junk is equal to A into 25,000 A's pattern. Oh God, what happened? Shit. Okay. Thank God. So okay, I'm using subdomain text. Now I'm going to create 25,000 A's. Pattern is equal copy just make sure we have created. I have pasted correctly. I'm going to print the length of the pattern. Okay, it's 5,000. Sorry, my bad. Oh, it's okay, perfect. Now we need to create the M3U file. Is equal to just as you know, I'm too lazy. Overflow f dot write of. Now overflow is equal to, now we are both concatenating this junk and pattern. Junk consists of 25,000 A's and the pattern junk plus pattern. Okay, write of overflow f dot close. So one thing I need to say is you can just send to application like just as usual string, or you can convert into bytes. I suggest you to convert into bytes and then send to the application, because it's a local buffer overflow. You may not get errors, but when you are doing some FTP server overflow, then you need to write some network programming, socket programming code, and then you need to send it to bytes. Even if you send it as a string, you get errors. You can try that. So to convert into the bytes, I'm using physical junk.encode of Unicode escape. So this will convert the 25,000 A's into the bytes. Same. Okay. So now I have overflow is equal to junk 25,000 A's, and the pattern is just, okay, let's say print file created successfully. Okay, it's my exploit document. Overflow. Okay, where is overflow? Here it is. Run. Paste. Boom, application crashed. Let's check EIP and ESP values. EIP points to this address. Sorry, ESP points to this, which is J7 capital BJ. Am I right? Yes. And take a look at EIP also, which is for capital B J small j cap 5. There are 4 bytes difference between EIP and ESP. Note that point also. Points to 4 capital B J 5. Now we need to search for this. Copy, go to pattern creator. Okay, 1064. Not that. So in the 1064 part of pattern and also this junk, we are getting EIP. So what I can say is 25,000 plus 1064 is equal to 26064 4. Okay, we can override with this some just junk, and then we get EIP. So let's do that. 64, and also there are 4 bytes between EIP and ESP. I'm going to junk with a I'm going to fill the junk with A's and EIP with B's. Changing them into bytes, and let's call the space between EIP and ESP as X into 4. Now ESP, let's say C. Okay, I have the junk to 6064S and then EIP and the space between EIP and ESP, and then ESP with 4 C's, and then let's say junk 2 is equal to. Okay, before I have explained in the PPT the NOP instruction, which means nothing. We are going to use that here. It's just, let's say 2000. Okay, we are having the 26064S, and then now EIP plus space plus ESP plus junk 2. Let's see, if I'm right, EIP should point to B. Yes, exactly, EIP points to B, and then ESP points to C. Just foreign stack. Yes, ESP, exactly. These are 26064S, and then EIP and the space between EIP and ESP and the ESP. Fine. Now EIP points to BBBB. We have the CCCC in ESP. We can place our shellcode here. We have so many knobs here, so we can place our shellcode here and then make EIP to jump to our ESP, which is the starting of our shellcode. Then our shellcode executes. It's just simple changing EIP into this address will not make exploit reliable. We will use the jump instruction. For that we use mona modules. Okay, when you type the mona modules and hit enter, you can see all the DLLs used by the program. As you can see, just for now I am finding the rebase for. Okay, okay, in this you can see this is the application DLL msrm filter 03.dll. It has everything for us. No rebase, no SafeSCH, no ASLR, and so on. Okay, we will talk about SafeSCH when SCH exploits. Now go to my computer, see program files. Where is that ECRMT? Okay, ECRM to MP3. You can see what is the filter 03. Filter 03. Okay, I'm going to restart the program. Now we need to find. Sorry. We need to find in the DLL the addresses of the jump ESP instruction that we want to overwrite in EIP. to specify ESP. Okay, I have this location. Let's mark it. Generally generally we will look for the application DLLs, because application DLL, if we can use those instructions, we can use the addresses, the exploit will be readable. Or you can use kernel DLL 32.dll or ntdll also, it's your wish. Copy. Now I'm gonna yes, okay. Okay, you can structure.pack of capital I, which will be using for Little Indian. Okay, we are packing the address as the Little Indian. It will already pack in the bytes, so we no need to convert into bytes. Now EIP points to jump ESP. Our program controls flows from EIP to ESP and executes the C. So C is not meaningful. Let's put some knobs, say 20 knobs, and let's put a breakpoint. So whenever we open the overflow.m3, we should hit the breakpoint and some knobs. I don't think as knobs has some different kind of instruction, just those are knob, no operation, which just continues. So I think we are fine. So okay, junk EIP space ESP. Okay, did I run the program? Yeah, I have. Yeah, okay, I have already run the program. Here it's okay, input, and we can see breakpoint. Perfect. Into 03 interrupt 3, which is the breakpoint. You can see these are all the knobs we have put after our breakpoint. Now let's replace our breakpoint with our calculator shellcode. We can generate using the MSF Venom Okay, is that the correct syntax? Okay, I have already have the shellcode of the calculator, which pops a calculator. Okay, so I'm renaming this into shellcode because we are executing the shellcode. Okay, shellcode everywhere. Okay, shellcode calculator it pop. I think it's fine. Okay, I need to restart the program. Okay, it should open the character creator. When I load the file, it should pop up the character creator. Okay, done. Okay, in this way you will. Okay, thanks for watching, guys. In the next tutorials I'm going to show you different techniques how to jump to a shellcode, and also some tutorials on fuzzing and code caves, etc. Make sure you like the video and subscribe and share it to your friends. Thanks for watching, guys.